control panel to pinpoint the instrument probe that detected the problem. Correct the problem, and the line starts rolling again. And then there are the drilling and reaming operations on the block, hundreds of them, with enough instrumented probing to make certain the holes are positioned correctly and drilled to the right size. Some machining is so precise that heating elements are used to keep the tools at a constant temperature. At the completion of the rough and semi-finish, machining and drilling operations, spot checks for all dimensions to this point. The idea is to detect and correct problems as they occur, not have them show up on the engine test stand. Next, the finishing operations, a major key to a reliable, smooth-running engine. For example, finish boring on crankshaft, camshaft, and distributor openings simultaneously, so that final alignment between the three will be precise for durable, trouble-free engine performance. But you don't leave it there. You check every engine to see that alignment is perfect. Cylinder bores are honed to micro-close tolerances. Again, a 100% check for exact dimensioning. Find any discrepancies now, before the engine is assembled. And then, even with the extremely precise bore sizing, each bore is marked for matching with the corresponding size piston. The finished engine block, built and tested almost completely automatically for uniform, consistent dimensioning. But now, people take over, make certain that machines have done their jobs, that each engine is right. Crankshafts follow the same automated multi-step process as engine blocks, from castings to finely finished shafts. Crank pins are machined one at a time, unique in the automotive industry, for better rigidity, a longer lasting engine. Automated machining and drilling ensures uniformity, and the continual gauging at each station calls a halt to the operation if problems occur. Handling, fully automated, no damage during production. Main bearing finish, critical to engine performance, not only is measured as it's done, the measurements are displayed and recorded. Final process, crankshaft balance, so critical to engine life and smooth operation. It's fully automatic, just the right amount of metal removed. With the crankshaft right, the assembled engine can be finely balanced. And then you check 28 dimensions electronically. Computer controlled, the whole operation is automatic, right down to an analysis of any problems that turn up. Many other operations contribute to a reliable engine, some of them unique to automobile engine production. For example, combustion chambers are completely machined for consistent and predictable fuel burning, better performance, and ensures emission control to government standards. Engine components ready and right, time now for assembly, with gauging and inspection all along the way to make sure the correct fitting of part to part takes place. Major components such as pistons, rods, and crankshaft in place, the engine is balanced to 1/2 inch ounce by drilling away metal in the counterweights. Result, a smooth, quiet engine, a long life engine. Every engine gets this treatment. Now, gaskets bonded to oil pans and rocker arm covers to prevent oil leaks. All the dozens of components, distributor, timing chain, carburetor, everything that attaches to the engine goes on. Topped by a spark plug gap check so that the engine will run smooth, perform. And then every engine is started, run, and inspected for proper operation. Finally, an air check to make sure there are no water or oil leaks. When the engine goes to the car assembly line, it's right. The differential, another example of automated production for uniform high quality. A computer monitors the entire differential case line and stands ready to diagnose any problems that crop up, present a quality analysis, all on a moment's notice. When components are precisely built, assemblies just have to follow suit. At the same time, engines and other components are being fabricated. Sheet metal is in production. Bumpers begin their lives as sheet steel, then move through a series of forming and trimming operations. Before chrome plating, a careful buffing. It improves durability and is the beginning of a gleaming, satin smooth finish. Hoods, inner hoods, fenders, they also are born from steel, formed by giant presses and dies into the smooth, simple lines called for by stylists and translated by engineers into steel panels. The secret of a good paint job is priming, so you use the latest method, ELPO. It deposits paint through electrolytic action, very much like a plating process. Gets down into every crack and crevice for a uniform coat. When it comes out of the tank, the paint doesn't run, so there's a uniform thickness. No need to sand thick spots, take the risk of exposing the metal to corrosion. Temperatures, solution strength, electrolytic process, all monitored with an automatic cutoff if anything varies beyond the normal. If a problem arises, you find out now. The printout screen tells you what the problem is, and it's corrected right away, before final painting. Automatic finish painting. It's uniform, consistent, matches colors between front-end sheet metal and the body of the car. If an imperfection is found, the part is pulled immediately, and another hood or fender of the right color is put on the conveyor to join the designated body on the assembly line. A vapor reflow technique permits minor in-plant paint damage to be repaired as good as new. The paint actually reflows and mixes, becomes a part of the original finish, and it stays that way. The body plant, Valley of the Giants, as it is sometimes called, where huge stamping machines and presses transform sheet steel into floor pans, sides, tops, where the body of the car is put together. It is here, too, in the body plant, that interiors, the part of the car that people live in, come into being. When the body arrives at the assembly plant, it immediately undergoes a retest of all electrical items. Should a discrepancy turn up, it is repaired right now, not passed along to some future station on the assembly line. This is known as a built-in station concept, and it's the law throughout the assembly process. At the same time, the computer passes information regarding problems back to the body plant, so that they can take immediate action to correct the cause of the problem. Now, in response to individual customer orders, bodies are released from the holding area and begin their journey through final assembly. Accessories such as clocks and speedometers are electrically checked before installation into the instrument panel. And then the completed instrument panel is again tested for electrical continuity. At the same time, the check makes sure that the accessories ordered for that car, such as air conditioning or radio, are in fact installed and functioning. The same type tests are applied to the steering column and its 10 electrical circuits before installation in the body. All these tests are computer controlled for accuracy and reliability. It's a way of life and the road to reliability. It's the same story with frames. then it all comes together. All the right colors and accessories and options. Everything that's been ordered. Final assembly. Throughout the assembly sequence, the built-in station concept is the Bible. For example, brake systems are evacuated, pressure-filled and tested as the chassis moves down the line. Same thing with air conditioners. If any discrepancies pop up, they are corrected immediately. No waiting until the car passes through final inspection. No waiting for problems to accumulate. If necessary, the line stops. You build cars right the first time. This is the road to reliability. At the end of the assembly line, another major inspection operation. Any car with problems is shuttled aside and repaired, and the information goes into the computer. Where does all this information from these inspection stations go? It goes to plant management, and it goes right out along the assembly lines. A foreman can see exactly what his performance is, what his problems are, on an hourly basis, or at any time he elects to ask the computer for information. It's an excellent tool for working with people, solving problem areas, and identifying outstanding performance. 100% test of all electrical systems and lights for proper operation. Squeak and rattle check on a road simulator for all cars, not subject to weather conditions, replaces an outside track. A toe-in adjustment for the front wheels. The car locked in position until the setting is right, and the inspection ticket punched OK. Only then is the car released. Assembly operations and final inspections completed, the car heads for the shipping building a quarter-mile away. Transported by individual carriers, it eliminates handling or driver-caused paint nicks and scratches. Shipping inspection and a recheck of major systems for functional operation. One of the last steps on the road to reliability. For example, headlight aiming. Here again, the car is locked into place and not released until spot beams are set correctly on photocell targets. And then, brake tests for every car to see that the brakes are functional, stop the car straight. Final inspection completed, car okay, but the road to reliability doesn't stop here. Each morning, early, a management team selects 5 cars and goes over them with a fine-tooth comb, looking mainly for areas where the built-in station concept might be reinforced. Further, on invitation, Pontiac dealers from the surrounding areas visit the plant with their new car get-ready supervisors, select cars of their choice, and perform their own audits functional, appearance, and ride. It's a program that's in line with customer feelings, as voiced to their dealers. Built right, inspected to make certain they are right. The cars go to dealers as fast as possible because customers are waiting for their cars. All the effort, styling, engineering, production, inspection, shipping, aimed at just one thing, a quality, reliable product that will satisfy an owner. When it comes to reliability, Pontiac pours it on.
In a laboratory in Warren, Michigan, Detroit, an extraordinary engineering feat is taking place. Structural engineers of the Fisher Body Division of General Motors are testing new automobile bodies. But what is remarkable here at Fisher is that these bodies have not yet been built. They are mathematical models in a computer and scale models in plastic and metal built with the aid of computers. Yet, these tests tell the engineers what they must know about structural performance before building full-size test bodies. This use of computer design is the kind of innovative thinking necessary in the automobile industry today. The kind of thinking that has traditionally been the mark of the innovators from Fisher Body. If you were to go inside the network of plants where American automobile bodies are built today, you would see one of the most awe-inspiring sights in modern industrial production. Billions of pounds of steel every year, millions of pounds of aluminum and glass and plastic, of copper and lead and zinc alloys being formed and shaped and welded and assembled. Millions of yards of fabrics and vinyls being cut and stamped and formed and sewn, all destined to satisfy the personal mobility desires and needs of people here in the United States and around the world. From manufacturing and fabricating plants around the nation, they come. From countless suppliers, components of all sizes and shapes, to be joined together in assembly plants into the engineering and manufacturing miracle that is a modern automobile body. One new body assembled every 2 seconds, 1,800 every working hour. What can't be seen so readily in this ever-continuing cycle of new high-quality bodies for General Motors cars is the innovation that has gone into the design of the cars of the 1980s. Consider what an automobile body is. The part of the car that people ride in. The part they see and touch. The part that often makes the difference whether they are satisfied or not with their vehicle. For years, most American automobile bodies were separate from the frame. This concept gave larger cars a solid, sturdy feel. Many smaller cars were designed with the body and frame integrated into one unit. This concept took on new significance as the need to conserve fuel became critical. Regardless of body design, the key to saving fuel is reducing weight while retaining the basic structural integrity of the car. This means coming up with innovative weight-saving ideas without sacrificing the benefits that American car owners have come to expect and demand. Comfort, ease of entry and exit, adequate interior roominess, durability and reliability, safety, both for adults and children. Quality, overall value, and yes, good looks. The basic concept for each major new General Motors automobile comes from a project team of key design and engineering people. They determine the character of the car, and they guide the stylists as they create the package, establish the size, and develop the shape. It is a process that evolves out of countless discussions with engineers and other specialists from the car divisions, representatives from Fisher Body and top GM management. Aerodynamics are critical because some of the fuel consumed by an automobile is required to push air out of the way. So wind tunnel tests are vital in the early design stage. Special attention also must be paid to the interior. The designers and the engineers ask the question, what can be done to maintain interior roominess in a resized car? One way is to use the door space more efficiently with recessed armrests and controls, so there will be greater usable interior width. We can find more headroom by designing a one-piece roof liner that snaps into place and takes up less room. We can increase rear seat legroom by redesigning the front seat structure into a thin shell that is strong and will accept a comfortable full foam cushion. We can give the luggage compartment more efficient space by using flush tail lamp assemblies and lowering the floor of the trunk. Innovative ideas like these are basic to the project team's considerations before the final concept is accepted and approved. The end result is a product of the design staff, a full-size model of each new GM automobile carefully sculpted in clay, each dimension accurate to a fraction of an inch. But there is much to be done before this car will be built for sale to the public many months in the future. First, the innovators from Fisher must get the dimensions of each new model from the clay into a form that they can use to design and build the body. At General Motors, this is done by an electronic surface recorder that takes the basic contour dimensions right off the clay and puts them into a computer. The computerized surface information from the clay model is then transferred from design staff to Fisher Body via a computer communications link. With the surface information now in the computer and available to the various engineering groups that need it, the innovators from Fisher have what they need to go to work. Their job, very simply, is to transform the clay into steel and aluminum and cloth and glass and all the other materials that go into a modern American automobile. And at the same time, meet all the federal standards and requirements for economy and safety. And be sure